Hi, this playlist comprises 4 short videos addressing the subject of regular sequential circuits. In this first video, we will look at their basic concepts. After watching this presentation, I hope that you will be able to differentiate between the 3 main types of sequential circuits that are indicated here, and also to write a VHDL description for the basic building blocks that are used in this type of circuits. Now, in a combinational circuit, the outputs depend solely on the current value of the inputs. On the other hand, in a sequential circuit, the outputs depend not only on the current value of the inputs, but also on their previous values. And what this means is that sequential circuits have memory in the form of internal states. So the outputs of the circuit then depend on the current value of their inputs, but also on the current circuit state. We will focus our attention on synchronous sequential circuits, which are the most common type. In this type of circuits, the storage elements, the D-type flip-flops, are controlled by a single clock signal. Now let us start by differentiating between the 3 main types of sequential circuits that we will consider. The first type consists of regular sequential circuits where the state transition is highly regular. A binary counter is a good example of this type of circuits. When the state transition is less regular, we will be in the presence of so-called finite state machines. A sequence detector can be referred as an example, since the state transitions in such cases do not follow a regular pattern. Again, we will see an example in soon. And finally, a finite state machine with data path corresponds to a more complex type of circuits that we will look into later in this course. In such cases, we find a combination of regular sequential circuits and also finite state machines, and also a combination of structures and routing networks. So the regular sequential circuits, which is the first of these 3 types, comprise counters and shift registers, for example. And in the case of the example shown here, which corresponds to a binary counter, you can see that the state transition diagram indeed shows a very regular pattern. Now, in this case, it is an up counter, but it would be the same if it was a down counter or even a bidirectional counter. We would still have this highly regular state transition. Now, in the case of a finite state machine, which is the second type and the example that we are looking at here, you can see that the state transition follows a less regular pattern. And this means that it cannot be implemented using such a circuit as a counter or a shift register. So the combinational logic generating the next state is a far less regular structure. Now, the third type, as I said, we will look at later on in the course, but this is just to give you an idea of the difference between finite state machines and finite state machines with data path. So in this third type, we will be dealing with circuits of much higher complexity, where the state diagram cannot be implemented just using these small complexity circuits that we saw in the previous slide. In such cases, what will happen is that we have the so-called controller of the circuit, which in itself consists of a finite state machine, and then a data path that comprises a number of regular sequential circuits, eventually finite state machines as well, combinational blocks, and routing networks as well. So, common to all sequential circuits, we have the need for a basic storage element which can be used as an elementary memory. And that is the role of the D flip-flop circuit, which has the function table shown in this slide. Let's take a look at its VHDL description. In this case, we can see that the entity description shows 3 inputs, which are all of the standard logic data type, and 1 output, which is also standard logic. The behavior of the circuit is described in the architecture body in the form of a process, and the statements comprised in this process offer a very self-explanatory description of its behavior. The process is activated whenever there is a change in the clock or reset inputs. When that happens, and because the reset input is dominant, we must set the output to 0 if reset is active. Otherwise, if the clock transition corresponds to a rising edge, then the output will be updated with the current value of the input. And that's it. Thank you for your attention.